Hello, everyone, and thank you for joining us today. Welcome to day one of Megger's Virtual Cable Best Practices Seminar. My name is Michael Fleischer, and I'm the Digital Marketing Specialist for Megger. I'll be acting as the moderator for today's presentations and supporting you on any technical issues or questions for our presenters. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of each presentation. Today we will have two separate presentations with their own Q&A sessions, so please stick around after our first presentation concludes. The presenters today will be Sergio Razio and Javier Ruiz-Leva, both being Megger's Cable Fault Location Test and Diagnostic Area Sales Managers. To assist with our question and answer session today, we will have Henning Oetjen, Product Manager for Cable Product. All right, let's go ahead and get started. Thank you so much for joining us today, Javier.
Thank you, Michael, and thanks to everyone for attending today's seminar. Let's start doing a quick review of the agenda for this short 15 minutes presentation. We will go first through the basics for medium voltage cables, and we will analyze what is the BLF test, the parameters, and the goals. Also, we will do exactly the same for the 10 delta and the partial discharge test. We will see what those tests are and what parameters are involved and what are the goals of the three test methods. Well, let's start with the basics for medium voltage cables. We are seeing in the slide the classic single-phase cable in which we have a center conductor that could be of copper or aluminum material. Then we have this inner semicon layer. Next, we have the main insulation of the cable. We will continue with the outer semicon layer. Then next we will have the neutral concentric shield of the cable, and finally we will have the jacket or sheet of the cable. Regarding the constructions of the cable, besides the previous one that was the single-phase shielded medium voltage cable, we can have the three-core cable in which we have 3 conductors, and each one with its individual shield. And also we have the belted cable. In this case, we have 3 conductors, but we have a common shield. So this is the different cable constructions we can have in medium voltage cables. Regarding the insulation for medium voltage cables, we have the solid-dielectric or the polymeric insulation. You can see in the left of the slide the EPR and the XLP insulation, the XLPE insulations. They are maybe the most common insulations that we have nowadays in the medium voltage cables. And in the right, you will see the paper insulated cable. That is also, we can find them also very often in medium voltage installations. In terms of the faults for medium voltage cables, we should distinguish between local issues and global issues. A local issue will be restricted to a portion of the cable insulation or its accessories. And mainly, the local issues are related with poor workmanship or installation problems. By the other hand, the global issues are spread along big segments of the cable, and they are related with the aging conditions of the insulation of the cable. So depending on what problem we are dealing with is the test we will choose. For instance, if we are dealing with severe installation or manufacture issues, we can use the BLF test. If we are looking for incipient installations or manufacture issues, we can use the partial discharge test. And if we are looking for old cables and we want to know which cables are the oldest in my population of cables, we can use the 10 delta test. So depending what we are looking for is the test we need to choose. What is the BLF test? Let's start talking of BLF test. The BLF test is fundamentally an AC over voltage test. It's also called AC hypot. And the frequency we use for this AC over voltage test is 0.1 Hertz. In the BLF test, some standards allow to decrease the frequency. Some other standards don't allow to do that, okay? But well, normally we will say that the official frequency for the BLF test is 0.1 hertz. And the BLF test is pretty much like a pressure test. And we will apply a voltage above operating. The voltage will be prescribed by a standard, for instance, the IEEE 400.2, and we will look for a breakdown. What we want to do during a BLF test is convert in fault the severe issues in the insulation or the accessories of my cable. We use the BLF test as commissioning test or after repair test, and is a go, no go, or pass fail test. So we will have a limited diagnostic information during the BLF test. The parameters involved in the BLF test are the wave shapes. We have mainly two wave shapes: the sine wave shape that you can see in the graphic in the left, and in the right we have the cosine rectangular wave shapes. Of course, both technologies, both wave shapes have advantage and disadvantage, and maybe we'll go through them in the next slides. The test voltage that we use for the BLF test will be between 2 times U0 and 3 times U0, where U0 is the rated RMS phase to ground voltage. And the test time will be between 30 and 60 minutes if we are using, for instance, the IEEE 400.2. The frequency must be 0.1 hertz, but in the BLF test we have the option to decrease the frequency. For instance, when we want to test very, very low cable with sinus units. The goals of the BLF test are convert in fault a severe problem in the cable insulation and its accessories during the test time, and at lower energy in comparison with the service fault. So this is very important, and we will do this under controlled environment, and we will avoid, of course, collateral damage. Now let's continue with tan delta test. What is the tan delta test? Well, the tan delta test is a global method of testing cables to provide an estimation of the remaining life expectancy of the insulation. We know that there is a correlation between an increase in 0.1 hertz tan delta and a decrease in insulation breakdown voltage at power frequency. So the tan delta is based on BLF technology. We will use a 0.1 hertz BLF sine wave shape. We cannot use the cosine rectangular to do a tan delta test. Must be a 0.1 hertz BLF sine wave shape. It's a diagnostic tool, so we will have 3 assessment criteria: the mean value of the tan delta, the delta of the tan delta, and the standard deviation. And the results can be compared with the tables in the IEEE 400.2. And also is a prescribed test method by the IEEE 400.2 2013. Very important also for the tan delta test, as we can use, as I said, the BLF sine. We must use the BLF sine, and the frequency must be 0.1 hertz. We cannot decrease the frequency when we are doing a tan delta test. We can do that in the BLF test, but we cannot do that when we are doing a tan delta test. The frequency must be fixed, and it will be 0.1 hertz. The parameters involved in the tan delta test is the wave shape. The wave shape must be sine, as I said. The test voltage, will apply 3 voltages steps: 0.5 U0, 1 U0, and 1.5 U0. This is according to the IEEE 400.2. The test time will depend on the measurements we took per voltage step. The IEEE recommends took between 8 to 10 measurements per voltage step, so it will take around 15 minutes. And I said in the previous slide, the frequency must be 0.1 hertz. 0.1 hertz. We cannot decrease the frequency when we're doing a tan delta test. What are the goals of the tan delta test? Well, detect the aging conditions in the insulation of the cable. For that reason, we will do the tan delta test in all cables, at least cables that have been in service for 5 years. The goal is to alert to critical aged cables before in-service fault and with up to 1 to 2 years notice. And of course, also to help target worst cables first. Now, let's continue with the third method, that is the partial discharge test. The partial discharge are little electrical sparks, and they eat the insulation of the cable. And generally, a partial discharge test, generally, I will say, is a non-reversible process. We have exceptions for this, okay? For instance, in the paper insulated cables, we have exceptions. But normally, in general, we will say that the partial discharge is a non-reversible process. Therefore, they will initiate the final cable fault. So how we do a partial discharge test? Well, we will apply a high voltage to excite the partial discharge in the cable and its accessories. We can use different wave shapes. For instance, we can use the damped AC. This is one of the wave shapes we can use. We can use also the cosine rectangular slope. Not all the wave shape, only the change of polarity is the slope when the change of polarity happens in the wave shape cosine rectangular. And also we can use the sine 0.1 Hertz BLF wave shape, okay? We will measure the partial discharge activity in the cable. We want to measure what is the level of the PD activity in my cable, but also I want to localize the PD activity spots in my cable. As we can see in the graphic at the bottom of the slide, we can see that we have a cable of close to 6.5 kilometers, and we can see partial discharge in the phase A up to 20 nanocoulombs at the beginning of the phase A, and in the phase B and C, we can see close to 2 kilometers partial discharge in a joint. Okay, so this is the idea of the partial discharge. Not only measure the PD activity, the level of the PD activity, we want also localize the PD activity spots. What parameter we will measure during a partial discharge test? Well, the charge, of course, the amount of charge, the intensity of each dielectric breakdown, and we will typically measure in picocoulombs. It could be also that we'll measure in nanocoulombs, but typically will be picocoulombs. We will measure also the time the signal from the breakdown takes to reach the sensor, and then we will determine the distance to the partial discharge spot. We will measure also the voltage, the applied voltage. We know that there is a dependency of the partial discharge with respect to voltage. For instance, if we start to see PD activity at 0.8 U0 in the partial discharge measurement, and we increase the voltage, then the level of the partial discharge will increase. So for the reason it's important to see the relation between the voltage, the applied voltage, and the level of the PD of the partial discharge. Also very important is the partial discharge inception voltage, that is the voltage when the PD activity starts in the cable, and the partial discharge extinction voltage, that is the voltage when the PD activity stops in the cable. The goals of the partial discharge is to detect improper installation, manufacturer defects, and third-party damage. Nowadays, the partial discharge is mainly used to detect or to see for poor workmanship issues. It will provide an early warning of the incipient faults, and we will have the possibility of remedial repair or replacement action during a scheduled outage. So this is what is the goals of the partial discharge. And now we will continue with the next topic, that is the tan delta, best practices on tan delta, and it will be presented by Sergio Resso. Michael, if you can pass the control to Sergio, please.
Sure thing. Sergio, are you ready to receive presenter control? Oh, Sergio, we might still have you on mute.
Yeah,
There
Yes,
we
I'm
are.
here. Okay.
All right. Wonderful. Presenter control is heading your way.
Show my screen. And from
Perfect.
beginning. There we go. And I think I erased the slide on accident.
Yep, we're okay.
So thank you, Javier. Thank you, Michael. Thank you, everybody, for joining us today, as my colleague has mentioned. So what we're going to do is go into when to use tan delta. Of course, it's typically used on age cables, 5 years and greater, and we also use this to detect aging condition change and dielectric properties of these said cables. So as you can see in this picture here, to my right, this is a cable tray with old cables sit into it, a service stage cable. It's also be used as part of the cable maintenance strategy. It's going to alert you to critically aged cables before in-service fault and up to 1 to 2 years notice. It's also going to be used as part of a cable replacement project. And where this comes into play is that it's going to let you target the worst cables first, and it allow you to have the best and wisest choice of the available money in which, depending on how valued that asset is, where you should spend your money first. Now we'll go into why to use the tan delta. Of course, this is a non-destructive test. It is very unlikely to fault the cable during or after this test. It's a diagnostic, so it can estimate the health of remaining insulation of an aged cable. And it's also to detect aging conditions and possible unclean accessories as well, albeit either a term or a splice. And then, of course, increase system reliability in the bulk insulation. What can it detect? It provides an overall condition assessment, estimate life lost in the cable insulation, and it can detect presence of water trees, contaminants in insulation moisture, degraded accessories, and oil leakage in PILT cables. If you look here at this picture, this is an example of a water tree in the insulation, and here's your semiconductive layer, your outer semicon, and your conductor, whether it be aluminum or copper. What it cannot detect is it cannot locate discrete problems, only that there is or is not a problem. As stated before by my colleague, this is a global assessment. What specifically the problem is, it cannot detect either. Is it a corroded concentric, a water tree, maybe a dirty term? Problems in the jacket or the lead sheath, poor workmanship, manufacturer defects, global measurement that does not localize. Basically, this is a leakage current measurement. Not basically, but that's part of what it is doing here. Theoretical approach is the simplistic purposes of the circuit represents a cable with a perfect insulation. If you look here, let me get into my animation here. If the cable insulation is perfect, then the resistor in my circuit, sorry, my webinar thing is blocking my words. Other words, and the value of resistance trends to infinite. This will mean that all the current in my circuit is a capacitive current, and then it is 90 degrees shifted to the voltage applied. As voltage here, there's my resistive, there's the infinite, there's angle, excuse me. Sorry. This is the, sorry, somebody's knocking at my door. Tan delta, represented here in this slide. Sorry, I'm going over to the next slide. Wave shape frequency. Sorry, we use a sine wave shape. Test frequency is at 0.1 hertz. Number of tan delta values, 8 to 10 per voltage step. Which voltage levels? Stepwise increase in voltage. So if you look here on the bottom right, step 1 is at half nu aught. Step 2 is at operating, and step 3 is at 1.5. Any questions? Okay, so why we need to use a sinusoidal wave shape. Here's the sinusoidal as you saw earlier. And then the difference is here on the right, the cosine rectangular. We don't have the phase reference between the current and the voltage in this cosine rectangular for the tan delta measurement as opposed to the VLF. And then in a purely capacitive circuit, the current leads the voltage by a 90-degree angle. As applied here, A is the voltage, B is the current, and then this is the time. Going into this, you're always going to use 3 voltage levels. So the 3 criteria are how you assess within the standard. And that's key because you want to be able to have all 3 of these to be in the standard. And also furthermore on that is that different dielectrics, different types of cables will mask other problems. So if you look here, this is 0.5, 1 times, 1.5. This is the mean BLF TD. If you look at our animation, this is the 8 to 10 values on between each step. 8 to 10 values all between each step. And this is the equation. Here is the differential VLF TD, which is the DTD, as per IEEE 400.2. And then it says here, it's tan delta, the behavioral to increase the voltage. Look here, this is the average of those 10. Oh, sorry, I went a little too fast. This is the average between these here, and these here. This is your value for the DTD. And then BLF tan delta time stability for the standard deviation is the difference between each measurement, all 10 in between each step is the standard deviation. As you can see on the scale as we grow up, this standard deviation is higher, and then so on and so forth. The assessment criteria is the measured values of the TD, DTD, and standard deviation are primarily influenced by the conditions of the cable system components. So historical figures, table 4 is the historical figures of merit for condition assessment of service age PE-based installations, e.g. PE, XOPE, and TRXOPE using 0.1 hertz. So this is the table in the 400.2. As you see here on the left is condition assessment, no action required, further study advised, and action required. VLF TD, so this is actually backwards from what we've shown, but this will be the first slide. Mean VLF TD at operating would be less than 4, would be no action required. 4 to 50, further study advised. Greater than 50, action required. This would be our DTD, difference in mean at 0.5 to 1.5. Less than 5, no action. 5 to 80, further study advised. Greater than 80, action required. And then VLF TD time stability would be, of course, standard deviation. Less than 0.1, no action. 0.1 to 0.5, further study advised. And then, of course, greater than 0.5, action required. Assessment criteria. So breaking those each action down, no action required means no indication of severe problem in the short term. The cable system can be returned to service, and the cable system should be retested at some later date, maybe 4 years. Further study advised would be additional information is needed to make an assessment, comparing historical TD results of the tested cable system. This is important because historical would mean that you've done this more than once in an aged circuit, not new, in an aged circuit. An example of this would be maybe a cable run that before had a failure, you added a splice, and so you had the data before the splice, and then you would have it after the splice. Additional diagnostics test, monitored withstand test, visual analysis of circuit components, and then of course action required would be poor insulation condition. The cable system should be considered for replacement for repair immediately. This is voltage dependency of the tan delta. If you look here, this is just like we were discussing a minute ago. This is on time. If you look at our table here, you have the red reference cable, which is new, the yellow, which is slightly service age, the green is moderately service aged at 2 years, moderately service aged at 3, strongly service aged. So if you look here at this scale, voltage dependency of the tan delta of the new and service age medium voltage XLPE power cables. Important factor for decision-making process is the tan delta, also called tip-up. So if you look here at this 1.5 times of this aged cable, you can see here how this is dramatic jump up from the new to the moderate to the service age to the slightly. Oh, sorry. And this is where those the values come into play. So there we go. How to interpret results. So this is a report section of the tan delta. This far left representing the tan delta values. This representing the voltages at each step. And then this is representing of the phases in each set. So phase 1, phase 2, phase 3. And if you look, this is a tan delta on good cables. If you look how they trend between the voltage ranges coming up. And then how we're going to interpret results here. So this is the same cable. One is in the rain and one is in the sunny day. So if you look here at the voltage kV is 12.7 here, 19 here, 25.4 here. Excuse me. Phase 1, phase 2, phase 3, this is your tan delta value at each step. And if you look here, 589, 602, 711, represented by this blue phase here in L3. Then you see the same exact cable here on the sunny day now, same voltage range, 12.7, 19, 254. Phase 1, 338, 388, 500 as compared to 589 in the rain. Phase 2, 343, 394, 477 as opposed to 602 in the rain. And then phase 3, 369, 426, 497 as compared to 711 in the rain. So tan delta is a measure of temperature and humidity. It's also a factor in this. How to interpret the results. So if you look here, this is a wet cable. If you see phase 1 is green, phase 2 is red, phase 3 is 3. Same scale, tan delta and voltage. Now, if you look where this starts, when the cable is wet, see how initially it starts high here on phase 3, and then as the voltage is applied and increased, you actually see a decrease, letting you know that it is water. So that's what this cable does here under an actual wet. Limitations of tan delta. In order to meet the standard, the frequency, as my colleague mentioned before, must be 0.1 hertz for tan delta. If other frequencies are used other than 0.1 hertz, and we cannot use the tables of the IEEE 400.2 to evaluate the tan delta. Another limitation is the limited length of the cables under test, around 3 kilometers. And then another major factor is when measuring hybrid insulation types on the same circuit, i.e. you have some EPR, some PILC, maybe some of it is XLPE, and you've tied that in. The different insulations will mask the defects depending on what insulations you have in that circuit. And these are the limitations of all tan delta values. And of course, if you're not using the 0.1 hertz and the 3 steps, there's no table to compare to. The tan delta is a scalar quantity, dimensionless unit. The measurement is a function of temperature and humidity, as I stated before, and it's the measure of the loss angle, ratio of resistive and capacitive current. As cables age, the insulation of the resistance decreases, the resistive current increases, and the angle increases. Compare this angle to the IEEE 400.2 2013 tables, and you are able to make the proper assessment. Excuse me. What we have here is our product list for BLF sign units with internal tan delta. So here we have a 45 kV unit and a 62 kV unit. All of these units have a built-in standard assessment reporting already in these units. So these units not only have the BLF technology with the sine wave, they also have the built-in tan delta, so no need for an external missile type connection or extra connections to be able to have your tan delta values. And all of the reporting that we just went over is also built into the assessment report. So for the end user, this is great because as you introduce what cable you're at and the voltages you're using, the standard is built in and it'll give you an automatic assessment. So making that an even easier unit to use going forward with your technicians and looking at data. This is a BLF and TD test using a graph to show you how the connections work. So if you look here, here's our box. This is your power cord for this actual unit. Your grounding, which is going to be usually at your single point, whether it be at your transformer or your connection, your switch. And then this is your high voltage lead to your conductor, whether it be NEMA hole, load break, or dead break. And then the return, which is always right outside the termination where it enters out of the termination. And of course, this is your single point. And this very simply is the connections to be able to take these measurements. what we have here is the top of the screen looking down at these units. As you can see, this is your jog wheel. This is how you control, it's your mouse. It's going to allow you to go into all the functions of the actual unit itself. This is your e-stop. Number 2 here is your power. Number 3 is your key interlock for lockout tagout. Green is your power on. Red is your power off. Number 6 is your USB. And then number 7 is your screen, which looks like this. And this is the actual control panel that you'll be looking at. So if you hear it's a BLF Sinus 45 unit, it is a date and time stamp for you so that you never lose that data. It has the standard that you'll be using in this particular is 400.2, 1.5 times. L1 action required. Of course, here's the BLF 10 Delta, and this is your jog wheel as you use your mouse. It's telling you the phases that you've already done, that you're grounded, and so on and so forth. This is doing a 10 Delta test. This is an actual data sheet. So once the test is done, of course, it's going to give you this automatic IEEE 400.2 standard assessment for you. Excuse me. This here is a report. Actually, let me blow this up. So if you look here at this report, this is a project cable information. So you can enter in your cable type, what it is, 1/aught, 220 mils, location, your start, your end, the voltages you're using, the phase you're on, cable size, so on and so forth. In your notes here, you can add obviously where your connections are, but also remember we're saying that tan delta is a function of temperature and humidity. You can put what the temperature and humidity is here too, so that as you see this data, you'll be able to know, was this actually affecting me? Was it raining on me? So on and so forth. If you look here, is this graph, just like we were showing earlier, but now it's in the report of this L1 phase. These are your voltage steps. And if you look phase 1, L1, voltage was 14.9, frequency was 0.1, capacitance was 43. Here's your average tan delta at 43.4. Delta TD was 52.9. Standard deviation is 0.71. Average tan delta result. And here it has all 3 of each phase or of each step. And your result, of course, is action required. And the criteria, it even breaks it down as to what criteria you are going to. And the inspector or user as you like. Here's another look at those same things. So this is the action results as this whole system works. Okay. These are the webinars about BLF TD that we have on the web. So this is the Megger.com webinar, the YouTube, and I'll leave these links up here for a few seconds if you would like to write them down or take pictures of them. But these are additional training.
And we'll also have those in the follow-up email going out tomorrow morning with a copy of these presentations and recording of the webinar. So don't feel too pressured to write these down exactly at this moment.
Thank you, Michael. Appreciate that. Yeah, I should have mentioned that. They will be at the end of the presentation. This is the contact information for me, Sergio Razzo, srazzo@megger.com, USA Sales. I'm officially over the Southeast region, but we are all a team, so we'll help whoever is in need. And then the questions.
Wonderful. All right, thanks a lot. So Sergio, we'll have you pause your screen here on questions so we can get into our Q&A real quick. As a reminder, we will have a copy of this presentation, the recording of the seminar, and any external links mentioned therein on an email going out to everyone who's in attendance right now tomorrow morning, so you can prepare for our second day tomorrow at the same time. Additionally, we will have a secondary presentation right after this Q&A session, which is going to be very short, so stick around. While we mention our Q&A session, we're going to jump right in and send our first question to Henning Ochen. Henning, are you with us?
Yes.
All right, wonderful. So our first question, Henning, is going to be, why do we use 1 Hertz AC test?
Okay, the problem with AC testing in the field is because of the reactive power you need to charge a cable every 8 milliseconds and discharge it, you would need a huge power supply, which is not practical for field testing. In a factory, they can do it. You know, the cable factories do that with 60 Hertz. But in field testing, that's why I people were looking for a method, an AC test, that would, and operating at a lower frequency, you cut the amount of power required by the ratio of the frequency. So if you go to, from 60 hertz to 0.1 hertz, you cut it down by 600 times. And that makes it feasible to do an AC test in the field.
All right, thank you, Henning. While I have you, I'm going to send the next question to you as well. What are the pros and cons for single conductor versus multi-conductor cables?
That is I don't know, there is not a right or wrong answer. It's just an answer. Typically old cables, initially, three-phase cables, they were all paper insulated cables. They were what we call sector cables. So they were taped conductors and shaped conductors. And what it really did is it allowed a very small cross section for a cable to be put in the ground. And that is clearly an advantage of a multi-conductor cable, that it has overall a smaller cross section, especially when it's a sector cable. And sector cable you can figure as if you take a circle and you cut it in three equal segments. That is what a segmented cable looked like. Today, when you go to solid dielectric cables, those cables are not done this way anymore. And most of the time, they use three individual cables that are triplex together. That still gives you a little smaller cross section than having three individual cables. There is not really, I think, a advantage, disadvantage of multi-core with a single core, but it is today, sometimes it's a problem when you replace old paper cables with XLP cables, that the conduit or the ductwork that's available will not allow to put the new cables in. And that's why some companies have gone to what's called a reduced insulation wall, so they can use the old conduit.
All right, thank you, Henning. Javier, I'll send this question over to you. What is the relationship between TD and breakdown voltage of cables? Could you brief this out for us?
Well, indeed, it's very untypical that we have breakdowns during a Delta test, okay? We need to keep in mind that the IEEE 400.2 reduced the voltage for the Delta test from two times G0 in 2004, that was the standard. And in 2013, they reduced the voltage to maximum 1.5 G0. So it's very untypical that we will have a fault during Delta test. For the BLF test, it's very often that sometimes we have faults during the BLF test. There is a paper or an article of the Dortmund Wasser und Energie, that is a German company, in which they established that for the BLF test, during the first half hour, we have almost 75% of the faults, okay? But for Delta test, I will say that it's very untypical to have faults.
But maybe just as a brief comment on this, there is not a direct relationship between 10 delta value and breakdown. You cannot say if I have a 10 delta of X, that means I will have a breakdown of Y, okay? There's no direct relationship.
All right, thank you. Henning, what is the reason behind unequal leakage between phases on the same cable? Does this require you to perform diagnostic tests for a higher leakage phase during BLF high pots?
Well, I assume he has talked about a three-phase cable with three individual cables, and it's very common that all three cables will not show the exact same, let's say, dielectric properties, whether it's 10 delta or leakage current or whatever. And that has to do with the fact that when the cables are installed, they're not actually treated identical. So one cable could get some damage that the other two phases don't get. So when you have one phase that sticks out, that is much higher in, let's say in this case, 10 delta, that's what we talk about here, then you would have to see what it can mean. If we look at the 10 delta criteria, like Sergio was pointing out, the tip-up factor is a very important one. And so if you have a large tip-up, that could suggest that you have somewhere in that particular phase some ionization, which could happen maybe in a splice, or could happen in a termination, or theoretically also in the cable, but typically not. Where on the other side, if you just had a elevated 10 delta, but the slope of the 10 delta or the tip up is very steady, that means it's just the baseline of that particular cable, for whatever reason, is higher, but it's less dangerous, by far less dangerous compared to a high tip up. But whenever you get a high tip up in one phase, you should do more testing and think about, what it could be, and maybe do a partial discharge test, or sometimes even could be as easy to try to change out a termination, because when termination, especially when they're exposed to the elements for a long time, maybe 20, 30 years, they could also develop some deterioration that could lead to a high 10 delta, a tip up, okay?
Thank you, Henning. Javier, can any cable test be done on an energized cable?
Well, in the case of the BLF test and the 10 delta test, there is no way. I mean, we need to de-energize the cable to connect our power source, or BLF. In the case of the next topic, that will be partial discharge, and we will see that there is two ways to do the partial discharge test, that is the conventional and unconventional. And in the non-conventional, you can measure partial discharge on energized cable, okay? But for the BLF 10 delta and for the conventional partial discharge measurement, you need a de-energized cable.
Thank you, Javier. Henning, can partial discharge detect the water ingress in the straight cable or joint? Is partial discharge sensitive to water ingress or a water tree?
Okay, we have to go back to what does partial discharge mean. Partial discharge is when you have a discharge in a gas, could be in air, could be in other gases, but so in order to get a discharge, you need a high resistance, because otherwise you cannot get a discharge. So because you have to build the voltage up, and then it basically flashes. So when you have water ingress, that does the opposite. Water ingress basically reduces the insulation resistance, makes it much lower resistance, and in that regard, it cannot, PD, partial discharge, cannot detect water ingress and cannot detect water trees. There was a big discussion in IEEE about this topic many years ago, and it's a very good write-up in the IEEE 400.3, which is a partial discharge field test guide about water trees and its relation to being able to use PD to detect water trees. It's not possible, okay? Because from the physics point of view, you need a gas discharge, and to get the gas discharge, you need a high resistance, and you don't have a high resistance with water.
Thank you, Henning. Javier, are there any standard specs that I can incorporate into my project specs?
Yes, of course. For instance, for acceptance tests, acceptance or maintenance tests, we can use the IEEE 400.2. Also for 10 Delta applies that standard. For partial discharge, we can use the IEEE 400.3 and 0.4. For sure, yeah, there is multiple standards, not only in the IEEE, also in the IEC for tests, for commissioning tests, maintenance tests, and also for 10 Delta and partial discharge. Maybe we will add in the presentation that you will receive a slide with the most important standards that maybe you could use for your projects.
Thank you, Javier. Additionally, is a DC high-pot test a prerequisite for a VLF test?
No. Indeed, for XLPE and EPR cables, the DC high-pot is no longer recommended. Only we will be able to use, or we recommend to use the DC high-pot on paper insulated cables, okay? But no, for sure, if you are dealing with solid dielectric cables, EP or XLP, for sure, the only that you need is the BLF, and indeed the DC high-pot is no longer recommended.
Hello?
Hello, I think that we lost Michael. Well,
Oh, sorry, I fat-fingered my mute button.
Okay.
So it looks like we only have time for one more question before we have to move on to our next presentation. And I'm going to send it over to Henning. Henning, which is the best method of cable testing, VLF or DAC tests?
Okay.
Which is superior?
So let me make a basic statement. There are no good and no bad tests. There are different types of tests that are available, and any test method that is commercially available today has been proven to be good test method. The real question is, what are you trying to do by testing a cable? What do you want to learn about a cable? And in that regard, the BLF and the DAC tell you different things. So the DAC test, which is a partial discharge test, obviously can, like any partial discharge test, is an excellent test to find workmanship issues in termination and splices, because whenever you have splices and terminations, you're adding different type of materials on top of each other, which leaves the possibility of having gaps in between these layers, air gaps in this case. And whenever you have air gaps, you can get partial discharge, you can get a gas discharge in air. And that's why it's a very good test to do that. Now, the VLF test is a totally different test. The VLF test is a withstand test, and it can find out if the insulation is compromised in terms of its, let's say, insulation resistance. So if you have a low insulation resistance, that means if you go to the test voltage, you get leakage current. The higher the leakage current, eventually the leakage current will lead to failure, right? So that's one of the passes or the ways that cable can fail under VLF. But it can also fail if you have a gap, like a partial discharge. You get, if you go high enough in the high pot voltage, which you normally go, VLF testing is about on all cables 3 per unit. So you can create ionization current. And once you get ionization current, that means the same as your leakage current goes way up and it leads to failure. So it does different things. The PD test is a diagnostic test to hopefully in the field see whether you have a compromised cable somewhere, a spot that is compromised, and you can replace it or repair it before it fails. the BLF test in its basic form is a hypot, is a withstand test. It's go, no go. It either is good or it's bad. And so they do different things to it. And actually, there is a combination of the two, which is mentioned in 400.2. It's called a monitor withstand test, where you can use a hypot test and at the same time monitor, for instance, partial discharge, if you wanted to do that. What does that do? It's a very good method to check basically for all the possible defects, whether they are local defects, gas discharge, like in PD, or they are from resistive driven defects, like kinks or cuts in the cable, and that will be addressed by the VLF test. But there is no good or bad test. They tell you different things.
Thanks for that, Henning. So it looks like that's all the time we're going to put towards this Q&A session, and I'm not exaggerating when we have over 50 great questions that we really should be addressing right now. We just don't have the time, unfortunately. We'll try and follow up with you offline. If you have anything that's pressing that you think we would like to address a little bit earlier than we would normally, please reach out to us offline. We love hearing from you guys. With that, I'm going to send control back over to Javier Ruiz. Javier, are you ready to be presenter again?
Yes.
All right, here we are. All right, and we are good to go. Here, if you're going to open up another one, pause for us real quick. There we go. Perfect.
Okay. Okay. Thanks, Michael. So let's start talking of PD measurements. The first that we need to, maybe the first answer we need the first question we need to answer is, what is a partial discharge? If you go to Wikipedia, you will find this definition. A partial discharge is a localized dielectric breakdown which does not completely bridge the space between the two conductors of a portion of a solid or fluid electrical insulation under high voltage stress. If you see the drawing we have in the slide, we have two conductors in red, and in between we have the insulation. And inside of the insulation, we have an air bubble or a cavity filled with air. So what happens with this device is under high voltage is that the high voltage will build up inside the cavity, and we will have a breakdown, we will have a spark. And every time that happens, the walls that constrain the air bubble or the cavity will be carbonized. So sooner or later, we will have a fault between the two conductors. So this is the definition of a partial discharge. So when we will use partial discharge, when to use partial discharge? Well, we can use partial discharge as a commissioning test or after cable repair tests. And the idea or the goal is to find improper installation, manufacturer defects, or third-part damage. Partial discharge is especially good to find poor workmanship issues or manufacturer defects, or also installation problems. For instance, in somebody, if we have if the cable was bent too much, we will have a chance to find that kind of issues with partial discharge. As you can see in these pictures, the guy that fixed the cable in the holder exceed the torque, and for this reason they deformed the insulation of the cables. So for that kind of problems is that partial discharge will help us. So the partial discharge will provide an early warning of incipient faults, and we will have the possibility of remedial repair or replacement action during already scheduled planet outage. So how the partial discharge works? How the partial discharge works? As I mentioned, we have two ways to measure partial discharge: the conventional way and the non-conventional way. In the conventional way, we need to connect in the circuit between the power source and the cable under test a coupling capacitor. So we need to de-energize the cable in order to connect the coupling capacitor and the power source. And in the conventional way, when we use the coupling capacitor, we will work under the IEC 6270. Okay, so only when we work in the conventional way is allowed to speak of picocoulombs. We will see in the next slides that we will measure the partial discharge, and the unit of the partial discharge is the coulomb, and we will measure very small quantities of charge. For this reason, we will measure in picocoulombs, at the best nanocoulombs. Okay, but it's only in the conventional way we will need to calibrate the circuit. And when we calibrate the circuit, what we do is to put a calibrator at the beginning of the cable. We will inject a PD pulse in the cable, and what will happen is that the energy of the PD pulse we are injected with the calibrator will split in two. The first part of the energy will go back straight to the coupling capacitor, and the second part of the energy will go all its way to the end of the cable, and then will go back to the coupling capacitor. Then during the calibration, we will have two pulses, the first one and the second one. Okay, and this principle is the same that we will use to localize the partial discharge. We have, let's say, an air bubble inside of the insulation of a cable. So we will have the partial discharge. The energy will be split in two. Part of the energy will go straight to the beginning of the cable, to the coupling capacitor, and the second part of the energy will go to the end of the cable, and then will go back to the coupling capacitor. Then, as I said, we will have two pulses, okay? And these pulses will have a difference in time, the difference between the arrival of the first pulse and the arrival of the second pulse. So we will have a difference in time, and we will know the propagation velocity of the partial discharge pulse, so we can localize the PD spot in the cable. So is the way also is the way how we localize the partial discharge spots in the cable. So what we will measure during a PD test, the charge is very important, the amount of charge, which means the intensity of each dielectric breakdown, and typically we will measure in picocoulombs. Also, we will measure the time, as we saw in the previous slide. The time is very important. The time the signal from the breakdown takes to reach the sensor, meaning the coupling capacitor, and then we can determine the distance. The voltage is also very important because there is a dependency of the partial discharge versus the voltage, which means that if we detect PD activity at 0.8 U0 and we increase the voltage to 1 U0, the level of the partial discharge will increase. So that relation is also important. The other two parameters that are very important is the partial discharge inception voltage, which means the voltage when the PD activity starts in the cable, and the partial discharge extinction voltage. That is the voltage when the PD activity stops in my cable. For that reason, we recommend to increase the voltage step by step to detect or to find the PD IV and the PD EV. We have some guidelines for the partial discharge test. For instance, here we see that for aged cables in this guideline, we have that for instance, for a maintenance partial discharge test, the insulation must be PD free. So in a maintenance test, we should have not partial discharge in the insulation of the cable. But for instance, in the splices, we can allow up to 1 picocoulomb, okay? Sorry, less than 1,000 picocoulombs. That will be the limit, okay? For aged cable and the splices, we should have less than 1 1000 picocoulombs, and the same for the terminations, less than 1000 picocoulombs. So we have different guidelines, and we can use them to make a decision after we do a partial discharge test. Once we're done with the partial discharge measurement, we will have a complete report, and we can analyze the report in order to make a decision. For instance, in this table, we're seeing that, sorry, this is in Spanish, my apologies, but what we have in the first row is the background noise level, And you can see that almost is the same background noise level for the three phases. But in the phase L3, you can see that we have the partial discharge inception voltage was 19.8 kV, and the partial discharge extinction voltage was 10.4 kV. So by the other hand, in the phase L1 and L2, we didn't find any kind of PD activity. And the other very important parameter is the PD level and maximum voltage. In this case, we applied up to 2 times U naught. And you can see that in the phase L3, we get a PD level up to 5,788 picocoulombs. So this is the way we know that in the phase L3 we have partial discharge activity. It's very important that we have a good calibration. That is very important. Sometimes I see some reports in which the calibration was not successful. So this is very important that when we analyze a report of partial discharge, we see the calibration. And also it's very important, the location of the PD activity. If you see, we didn't have PD activity in the phase L1 and L2 for the reason we don't have any dots, blue and orange dots in the graphic. But in the phase L3, you can see that we get a lot of partial discharge at the end of the cable. The cable was 500 meters, so you can see very clear in this graphic that the problem was with the phase L3 and the problem was at the end. In this case, the level of the partial discharge, as we saw in the previous slide, and we can see right now, was 5,788 picocoulombs, which is above of the guideline we showed in the previous slides. So the guys that made this PD measurement should replace the termination of this cable. So what is important when we are doing a PD measurement? One of most important parts of the PD measurement is ensuring a good connection to the test object, okay? You are seeing one example of the connection of the setup, so the connection of BLF with the coupling capacitor, okay? And it's very important that during the connections, we'll be very careful doing all the connections between the cable under test and our unit, because a faulty connection could cause that we have an increased background noise level, or maybe we should create partial discharge in the circuit. We can put partial discharge in the circuit doing a faulty connection, or maybe we'll create a partial discharge at the near termination. The other problem we can have when we have a faulty connection is that no PD, no partial discharge activity will be measured at all, or will not be able to load the test object, okay? So it's important to have a very good connection between the PD equipment and the cable under test. We need to be always sure that we will connect the ground of the equipment on the same point as the return. If you see in this drawing, we have the high voltage lead of my cable connected to the cable under test, but the grounding is connected in this bus bar. And what we need to do when we're doing partial discharge test is that the grounding must be connected at the same point where we connected the high voltage test lead, the return of the high voltage lead, the return. So this is very important to avoid the antenna effect during the measurement. So always try to connect the grounding of your PD equipment in the return, in the point where you are connecting the return of your high voltage cable. Here we're seeing an example of a PD measurement. It was made in a cable with a length of almost 21,000 feet. The insulation was XLPE and the voltage was 35 kV. And you can see here in the horizontal axis, we have the length of the cable is 6.5 kilometers, which means around 21,000 feet. And you can see in the vertical axis the level of the partial discharge detected. And you can see that in the phase A, we have PD activity at the beginning of the cable, and the problem was that we didn't have a PD-free connection. For that reason, it's very important to have a PD-free connection between the cable under test and our high voltage test lead, okay? But in the phase B and C, you can see that at 5,900 feet, we have PD activity in the phase B and C. So when we open the, when we take out the splice, the joint, we saw that the guy that made this splice didn't put the mastic to seal the screw hole, okay? You can see here the screw holes, and sometimes in the connectors, you need to put a mastic to seal that holes. They didn't do in this splice, and that was the reason of the partial discharge activity in the measurement. For finish the presentation, I would like to show you some of the PD equipment we have in Megger. The first unit we have is the damped AC or the DAC 30 kV. This unit is only to perform the partial discharge test for 15 kV cables, and it's a unit that reaches up to 30 kV peak. And this is we use the damped AC wave shape to perform the PD test. The next units we have in Megger is the TDS-NT 40 kV and 60 kV. We have two models, and the first one, the TDS-NT 40, is for 15 and 25 kV cables, and the TDS-NT 60 is for 15, 25, and 35 kV cables. In the TDS-NT models, we have two options, two versions. The basic version, for instance, for the TDS-40, will have 2.4 microfarads, and the plus version we will have 4.8 microfarads. In the case of the TDS-60, the basic version will have 1 microfarad, and the plus version will have 2 microfarads, which means that if we have more test capacitance, will allow us to test longer cables. So this is the TDS-NT 40 and 60 kV, and we can do the BLF test and also the partial discharge test using the damped AC wave shape. The next unit, the next units we have. Sorry. The next unit we have is the BLF Sine 30. It's a sine wave shape technology unit. It's a very small unit. In this case, we can do the BLF test. We can also do the tan delta test, but in this case, we need an external tan delta attachment. We need an external tan delta attachment for the BLF Sine 34. And for the PD test, we will use this coupling capacitor that is our PDS 62. The next unit we have is the BLF Sine 45 kV. Is also a 0.1. This unit also uses a 0.1 Hertz sine wave shape. In this case, we can do also the BLF test, we have an internal 10 delta, as Sergio mentioned. We have an internal 10 delta built up in the unit. And if we want to do the partial discharge test, we need our PDS 62 also. And next, we have the TDM Sin 4540 kV unit. That is really a very interesting unit because we will have everything we need for BLF, 10 delta, and partial discharge. The TDM is a BLF Sin 45, but we can put a booster, and with the booster, we will have also the cosine rectangular wave shape to do the BLF test. And with the booster, we will have access to the cosine rectangular wave shape for the BLF test, but also we will have access to the damped AC for the partial discharge test. And of course, as this is a BLF sine wave shape unit, we can use the BLF sine 0.1 Hertz wave shape to do the 10 delta. So with the TDM Sin 4540 kV, we will have access to all the wave shapes, or the more important wave shapes that we use for the BLF test, for the 10 delta, and for the partial discharge test. We can have different options depending on what we are looking for. We can have the TDM 45 with 10 delta and BLF only. We can have the TDM 45 with the BLF, the 10 delta, and the partial discharge option. We can have the TDM 4540 with the booster only to have the BLF sinus and the BLF cosinus rectangular for the BLF test. And we can have the BLF, the TDM 4540 with the booster, which will allow us to do the BLF with the sinus wave shape, with the cosinus wave shape. We will do the 10 delta, and we can do also the partial discharge test with the sinus wave shape, with the damped AC, and with the slope of the cosine rectangular wave shape. So depending on what you are looking for, you can select the options for the TDM Sin 4540 series, and depending on what you're looking for, we can provide it. Okay, so it's very convenient unit. And the last unit we have is our BLF Sin 62. This is a sinus BLF, has an internal 10 delta, and also we can use the PDS 62 to do the partial discharge test. So this is the biggest BLF, the biggest sinus BLF we have, and this is our BLF sinus 62, and is a very nice unit because the cable is integrated in the unit, also the partial discharge, so it's a very convenient unit. And with this, I think that is all what I have for you guys. So I'm ready to have some questions if you have it.
Perfect. Thanks a lot, Javier. So before we jump into the Q&A session for this presentation, a few things I'm going to go over. First off, if you do have any questions you'd like us to address for this seminar, please put them into the Q&A box there on the side, or the questions panel rather. For those of you that are leaving, when you close the webinar window, a brief survey should pop up on the screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve our future webinars. On that survey, there is a field where you can also request a demo or quote on any Megger products. A copy of these presentations, certificate of attendance, along with a link to the video recording of the seminar will be emailed to everyone in about 2 business days, although I will try and aim to have them out by tomorrow morning in the Central Daylight Time Zone. You can also view previous recordings of webinars on our website at us.megger.com/webinars. And be sure to join us tomorrow for the second day of our virtual cable best practices seminar, where we will be covering cable fault location by underground infrastructure and tools. All right, so let's jump into our questions. The first one I have, I'm going to be sending over to our Henning Ochen. So Henning, factory PD is 5 PC max. Why so high a field for PD at 1000 PC?
Well, we have to distinguish between factory testing and field testing. The factory testing established a minimum acceptance criteria for the quality of the in this case for the splice termination. So they do factory testing. They say, okay, it has to be below a certain level to be acceptable, because how long is this piece going to be out in the field? It's not out there for 1 year. It's probably on average out for 30 years. It's the same like, you know, when you do factory testing on cables, you're testing at a very different level, because when the cable is new, it must take a whole lot more, so it can, under normal aging conditions, still function after 30 years, okay? So that's the biggest difference. The 1000 PC here that's mentioned, this was a number was given for, splices, and you have to be careful when you these numbers, you have to be a little careful about using numbers when you talk about PD levels, acceptable PD levels, because it depends what the splice is made from, or the termination is made from. If you have solid-dielectric, they have typically lower acceptable levels than fluid-filled termination or splices. So, but like I say, the 1000 in the field is a number that when you come to that number, when you measure that number, you need to do something about it. It's a warning flag, where the 5 PC is what it should be when it leaves the factory. So there's two different things. It's very hard to, really you cannot compare field testing to factory testing, because you're testing for different purpose. On the one side, you want to make a quality assurance test, which is the factory test, and the other one is you want to see what the actual field condition of it is, which can be will be a very different number, because you have all the aging and all the other influences that you experience during the life of the circuit.
Thank you, Henning. Well, I have you. How does the condition of the neutral or cable metallic shield affect the PD test results?
Well, that depends a little bit how you do the PD testing. Normally, when we do single-ended measurements, it doesn't have that big of an effect compared to when you do actually make measurements in the return circuit. Then the condition of the neutral is very, very important, and corrosion would be detrimental. But also on when we do single-ended measurements, if you have really a badly corroded neutral, it will create issues on your PD measurement. So it's not, especially also, for instance, on the really old cables where you had unjacketed cable, where the neutral was in contact with the earth or the ground, the earth ground. You could have big trouble, like with any other also dielectric type measurements on these type of cables. So if you have a jacketed cable, typically it's the condition of the neutral is good enough to get a good partial discharge reading.
Thank you, Henning. Javier, is it required to disconnect both ends of the cable during tests?
I will say yes. I would say that in the vast majority of the cases, we will need to disconnect both ends, because other way we could have some PD activity and at the ends, the far end, okay, for instance, and maybe we will not be able to know if the PD activity coming from the far end is because we live connected to cable or because we have problems in the termination. So I will say yes, and it's necessary to disconnect the cable for both ends.
Thank you, Javier. Henning, what is the proper time we should wait during applying high voltage to get proper PD activities in the case of different applied voltages?
Well, if I understand the question correctly, I mean, there is no waiting period. Once you bring the cable up to the particular voltage level you want to use to evaluate the cable for PD, the PD doesn't have a let's say a waiting time to start showing up. So it's not like you have a hesitation or you have to wait some time before it will happen. Typically, that's why you look at the inception voltage. When you bring the voltage up and you see what the inception voltage is, and then you look what the extinction voltage is. But there should be no waiting time, and I'm not aware that there's any difference between AC, BLF, and DAC. Okay.
Thank you, Henning. Javier, do you recommend to do PD tests in 2 stages? First before joints and termination while the cable is open, and the second test after joints and terminations have been completed but isolated from the equipment?
Well, it depends. If you have some concern in the way the cable was bring to your facility, if maybe it was not people of your company and you have no idea how they transport the cable from the factory to your facility, will be good to do a PD test before to connect the splices and the terminations. But I will say that mainly if you have a major issue, maybe if they I don't know, mishandle the cable during the transport, if you do the PD test with the splices and the terminations, you will be able to detect that problem. So it could be, I mean, it's okay to do a PD test before to put the splices and the terminations, but it's not, I will say that is not necessarily. I don't know if Henning, maybe you have other consideration regarding this question.
Thank you, Javier. Additionally, Javier, including time for lockout, tagout, disconnecting, and reconnecting each phase of the cable and performing of the test, how much time should be estimated to complete the test on a single cable?
I will say that under normal circumstances, under normal conditions, I will say that we will spend around between 15 minutes or 10 minutes per phase, okay? I will say that maybe 45 minutes will be the complete time we will need for a partial discharge in the 3 phases, okay, at the maximum. Of course, if you have some issues with the background noise level, or if you have a poor concentric, etc., maybe you can take a longer time. But I will say that between 30 and 45 minutes will be the time to do a PD test in the 3 phases.
Thank you, Javier. Henning, how does frequency of a 0.1 Hertz PD test compare with a 60 Hertz factory test? Is a 60 Hertz PD test more sensitive?
I think the question, I would change the question a little bit and saying it's not the matter of factory test 60 Hertz and field test 0.1 Hertz. It's in general the question is a 60 Hertz, whether it's field or factory test, a more technically a sounder test than a 0.1 Hertz PD test. And it's a loaded question. And I know certain people are in the meeting that will listen very careful to that. The answer is very simple. I think you have certain defects that are much more sensitive to, let's say, 60 hertz. I would call it power frequency, because power frequency, which means 20 to 300 hertz, has been proven equivalent to actual power frequency at 50 or 60 hertz. So I just want to say power frequency versus 0.1 hertz. So certain defects have shown higher sensitivity with power frequency than at 0.1 hertz. So overall, from a technical point, I think it's preferable to do PD tests with power frequency compared to 0.1 hertz. There are certain defects where the difference is not as big, but in splices and terminations, there have been shown examples where you know, a 0.1 hertz test might show no concern because the PD level is way above the inception voltage is way above operating voltage, and when you do the same cable at power frequency, you show that the PD level, the inception voltage, is already present below operating voltage, which means it's a big issue. So there are defects that react differently, and in that regard, I think power frequency is overall the more preferable method, because it eliminates this potentially masking of defects by using the 0.1 hertz frequency.
All right, thank you, Henning. Javier, my company has had some spare cable stored for over 20 years. What test would you recommend for this cable, if any, to be confident it will perform if ever the time comes?
Well, it depends how the cable was stored. For instance, if it was under the shadow, the temperature conditions, etc. But I would say that maybe the jacket, the first test I will do is to test the jacket of the cable, and then I will do a commissioning test, a commissioning BLF test. Okay, I will not concern about water trees in the cable, because for the water trees we need water inside of the cable and electrical stress. So I will not concern about the water trees, but maybe the jacket. For that reason, I will recommend to test the jacket, and maybe a commissioning test with the BLF, and maybe to see if some issues with the bend of the cable, maybe also the partial discharge test. That will be the three tests I will recommend.
I think Javier made a very important point there. It all depends how the cable was stored. We participated once in a test of a cable manufacturer who had retrieved from the field service-aged cable, and he had the same batch of cable in his own inventory still, and that was 15 years later. But those cables had been stored outside, and this was down in Texas. And the cables that were stored outside, even they had never been in service, they were aged much more compared to the cables that had been in service. So now you can imagine, if you store something out in the Texas heat over that number of years, there is a lot of aging going on in the polymeric material. So when we talk about aging, it's not only electrical aging, it's also temperature aging, it's UV aging, because they have a lot of UV exposure, and so on. So it's hard to say, because it all depends how this cable was stored over this period of time.
All right, thank you. Henning, what is the difference with measuring PDMV instead of PC?
Well, I think that question depends a little bit what you which method you're using. I think if you use a conventional method, you're typically using the PD, the picocoulomb, And if you use unconventional, then you use the millivolt. But you know, if you use the typical standardized method, which follow IEC 6270, then you would measure in picocoulombs, the apparent charge.
All right, thank you, Henning. Javier, could you please explain the term dB max?
Yes. First, my apologies because I took that measurement from some made here in Mexico. So in Spanish is descarga parcial. So it is first the D and then the P. In English should be PD max, which means the maximum partial discharge detected. Okay. So as you increase the voltage, you measure the average partial discharge you have in the measurement, and also you measure the maximum partial discharge you get in that specific voltage step. So DP is indeed PD max, maximum partial discharge in the measurement.
All right, thank you, Javier. And then I have a question for Sergio. Sergio, what is the preferred cosine rectangular or DAC?
Really depends on what it is that you want to do. So if you were doing, as mentioned before, where you were doing commission testing and wanted to perform the VLF or monitor to withstand test at the same time, you would use a VLF with the cosine rectangular for your commissioning test so that you're performing both tests at once. And then from an operational standpoint, what I like to say is, let's just say you're doing that test and at a splice or an accessory, you now see PD that you are at the levels that we were saying that you want to start questioning whether or not you should replace those. Then you can go into the damped AC, which is a pure diagnostics, to verify that that is PD you're actually seeing before you commit to actually repairing that. So it really just depends on what it is you're trying to do during that test. So damped AC is pure diagnostics. The CR with the VLF will be the accompanying PD with very low frequency during commission testing.
Thank you, Sergio. Henning, would you agree that we should approach factory test results after installation under ideal conditions so that we can use factory test values as references?
This brings back to a old question, and I think the common opinion on this is you cannot reproduce factory test results which are taken in a completely noise in a Faraday cage environment and expect to see the same approach in the field, okay? Because in the field you don't have this shielding. You have wherever the situation is, you have to deal with it. You have to deal with the background noise also. So that's why it's really I think to say use it as a baseline. I mean, there is no baseline because the factory has proven by doing their own test that it is basically not PD free, but it's down to that 5 picocoulomb level, and you can run a field test where you cannot have this perfect shielding, and you will have a certain background noise, and you still can see whether you have PD or you don't have PD. It's very obvious when you run the test. So the correlation between the factory test and the field test is really some people propagate. You know, they like to talk about it, but the question really is it it's really not achievable if you try to do it the same way, because otherwise, why even do cable manufacturers then have to do all the shielding in the factory if you could produce the same result, right? They could save a lot of money not having to do this. So I'm saying that these are two different type tests, and the one proves a quality standard and the other one proves a aging, sort of a aging or a workmanship condition.
All right, thank you, Henning. Additionally, what special PM testing and type of equipment would you recommend for low voltage or 600 volt feeder cables in operation for over 15 years?
But when you say 600 volt low voltage cable, there is a certain issue with it because they're normally unshielded cables. And when I have an unshielded cable, then I have a problem doing basically any type of test because I cannot establish a defined test potential or a dielectric, electrical field between the conductor and, so if the cable is direct buried, I could say, well, I could test it to ground. But so you can do a high pot test. But if you had a 600 volt cable laying in a cable tray, and the side that touches the cable tray, you have a ground potential, and the 180 degree opposite side is in air, so you cannot establish a test potential. That is not possible. So that's why low voltage cable testing is basically, unless you have shielded cable, low voltage shielded cable, is normally not feasible.
All right, thank you, Henning. I think we have time for one more question. I'm going to send it over to Javier. Javier, is PD tests sensitive to sheath fault or sheath damaged, or be sheath damaged if XLPE is good? Oh, Javier, we might have
Sorry,
you.
yeah, I was muted, yeah, my apologies. Well, remember, keep in mind that we will apply the voltage for the PD test between the center conductor and the concentric. So we are looking mainly for issues in the insulation of the cable or the splices and the terminations. So problems in the jacket of the cable will be quite difficult to detect with partial discharge. At least that damage will be related with other damage. For instance, if somebody bent too much the cable and crashed the jacket and inflicted mechanical damage to the insulation of the cable, then we will detect that problem, but because we have a mechanical damage in the insulation of the cable. But after the question, I will say no. With the partial discharge, we cannot detect issues in the shield or the jacket of the cable. We need to do the sheet test to find that kind of issues.
And to add to that, if you don't mind, that's where the tan delta would give you an indication of a sheath, because if the sheath is torn and water has gotten in, just as in the tables we used during the tan delta, you will see that there's wet cable, and then of course, like you said, sheath fault testing.
All right, wonderful. So it looks like that's all the time we have for our Q&A session, and indeed our first day of our seminar here. We apologize if we didn't get to your question today, but we will be following up with you offline. You're also feel free to reach out to us offline through our contact pages. We love hearing from you guys. We got scores of great questions. We'd love to just sit down and answer, but we have some time constraints to work out today. So if you could, please remember to answer our survey when you close out our webinar. We'd greatly appreciate getting feedback from you guys, hearing what we can do better, what you liked, what you didn't like. If you could, remember to join us tomorrow for our second day of our virtual cable best practices seminar. You can register for that and others at our website at us.megger.com. I'd like to thank you all for attending, our presenters for being here, as well as our panelists. I hope to see you guys tomorrow. If not, I hope you all have a great week.